Okay, welcome everybody to the session L on forecasting and uncertainty. So to all presenters, we will have 20 minutes to present their work with 10 minutes for Q&A after each talk. And if you have a question, please use the Q&A facility at the bottom of your screen to submit your question. If you are invited to ask a question, we will enable you to unmute your microphone. Please introduce yourself by stating your name and affiliation. And also please note that this session will be recorded. So our first presenter is Matteo Luciani from the Federal Reserve Board. So I ask Matteo, please could you share your screen?
All right. Can you all see my screen?
Yes, Matteo.
Very good. All right. So
you may need to do a full, I'm guessing a full view.
Yeah. Am I on mute? Yeah. Now you can hear me, right? Everything is good.
Everything is good. But is it possible to do a full view?
Yeah. Is it in full view now?
I don't think so. I think it looks
should be like this, no?
Okay, this is fine too. It will work. Yeah.
Sure. All right. Okay. So thanks a lot. Thanks a lot for attending this session and for inviting me to present here. This is so this work is basically about purging noise from inflation data and having a better read of what's going on into inflation. And let me stress, especially today, the disclaimer that what I'm gonna say today is what I think and what my research told me, not what the Board of Governors or the Federal Reserve System thinks. So you all know that the objective of the Federal Reserve is to maintain price stability, and this objective has been stated in terms of having a PCE price index, inflation in the PCE price index to hovering around 2% over the long run. And there are several challenges that, of course, the Federal Reserve has to face, but one of these is to avoid to respond to relative price changes, so sectoral or industry-specific price changes, or even worse, to measurement error, but rather to respond to macroeconomic shocks. So what you want to do is to respond to movements in the general price index of goods and services. And so it is very important for the Federal Reserve to determine basically on a month-to-month basis how much of price fluctuation are driven by macroeconomic factors or idiosyncratic developments of measurement error. Because although it's true that some of these idiosyncratic developments are relatively easily identifiable, this can be the case of changes in Medicare reimbursement rates or the change, for example, sometimes some index goes crazy, and this was the case in March 2017 of the index for wireless telephone services. So these ones are easy to spot, but not all of them can be easily traced to a specific phenomenon, and therefore a statistical model that is capable to filter out this idiosyncratic movement, this measurement error effects on inflation rates are very important for the Federal Reserve. And what this paper does is exactly this. So what I try to do, I try to disentangle the effect of common shocks on prices from the effect of idiosyncratic shocks on prices. And the way I do that is by using a statistical model that is entirely data-driven. Now, what I do mean with that, I mean that I'm using a model that basically there are no real economic assumptions, but instead it tries to speak the data, let the data speak as much as possible. And the methodology that I use works in two steps.
Sorry, Matteo.
Yes, sure.
We just see your title screen. So just wanted to make sure that the slides seems not to be moving. Okay.
Now
That's
you
fine.
see.
Yes.
Okay.
Thanks.
So we go like this.
Yep.
Okay. So the methodology that I use works in two steps. In the first step, so basically what I do, I analyze a large data set of disaggregated PCE prices. With large, I mean 146 disaggregated prices. And in the first step, I estimate a dynamic factor model on each disaggregated prices. Basically, in this way, I purge away the effect of idiosyncratic shocks from each disaggregated prices. And then I use the PCE weights to aggregate everything and to construct a common component of PCE prices. And in particular, what's going to be the main product of this paper is a decomposition of monthly core PCE price inflation, where with core I mean PCE price index excluding food and energy. And now first question you might have is why do I want to decompose core PCE prices where when the objective of the Federal Reserve is stated in terms of total PCE price inflation? And the answer is that at the Fed, at the board in particular, we are kind of obsessed with core PCE prices. Here I have a couple of quotes from Yellen and Blinder of two old papers, but essentially the focus is mainly on PCE prices excluding food and energy, because the assumption is that energy prices are basically driven by oil and the Fed cannot control oil, and food prices are driven by a bunch of idiosyncratic shocks like weather and other things, which the Federal Reserve as well cannot control. So our focus will be the index of the core PCE price index. The database goes up to the end of 2019, so I'm excluding all the part of the sample that is affected by COVID. And basically, you see on the left month-on-month inflation, and on the right year-over-year inflation. What I'm going to do, I will provide a decomposition of these two series, which will look like this. And the main result that I will emphasize and stress is that if you look at the period after the Great Recession and before COVID, basically most of the fluctuation in core PCE price inflation were driven by idiosyncratic phenomena. And the macroeconomic signal was essentially zero. So this is in a nutshell the paper, but without any further ado, let's jump to the methodology. And as I said, the methodology is in two steps. In the first step, I decompose each PCE price index inflation rates in two parts, common and idiosyncratic, where the common is driven by the macroeconomic shocks we are interested in. And in the first step, we're going to use, I will do this step with the dynamic factor model. Step number two is to aggregate all the common components. Now, I won't talk about step number two because this is a weighted average. We can discuss about the weights of PCE prices, but in the interest of time, I won't do that. And I would rather move quickly on the dynamic factor model. The model is in the end pretty standard. So it's a large dynamic factor model. So I have a large number of variables. And in the model, I have just one factor, but this factor is loaded dynamically. So within 3 months, each prices can load the factor whenever it wants within 3 months. And then the factor itself follows an autoregressive process. Now, there are, of course, a number of assumptions and some complicated econometrics behind that. I won't go into the details. I rather go into the main intuitions and the main assumptions that are relevant. And the main assumptions are 4. So the idea is that the factors and the shock that drive the factors are pervasive, meaning that they affect all variables. The idiosyncratic components are allowed to be both cross-correlated and serially correlated, but this correlation has to be limited. So the bulk of the cross-correlation has to be in the factors. Of course, the idea is that what is common and what is idiosyncratic is idiosyncratic, and these two objects are independent one another. And finally, very important assumption, the model is stationary. And to ensure that this assumption is satisfied, what I do, I use a relatively short sample, because the sample starts in 1995, because and the choice of 1995 is because from that period onwards, inflation data are clearly stationary. Now one can discuss whether it's 93, 91, 95, whatever, doesn't matter. The important thing is that one analyzes the part where prices are, where inflation rates are clearly stationary. So this is the model. The way it is estimated is with QML, with quasi-maximal likelihood via the EM algorithm. This is pretty standard. I mean, there is nothing particularly new, but I want to take the opportunity to briefly mention a work of mine together with my friend Matteo Barigozzi. We have been working on this estimation method, and we have added some new result to the literature, in the sense that now we have improved convergence rate, the asymptotic distribution, test of hypotheses, and more results. So what I will do is can be estimated, is consistent even if the distribution of the shocks are not normal but have fat tails. I mean, it's in summary, it's not a problem. So this is the methodology. Another important part of this work is the data set. Now here I could really go into many tiny and relevant details, which I will try to summarize. As I said, I have 146 disaggregated monthly PCE prices. And the characteristic of this data set is that each price is constructed out of a different data source. Now, why this is relevant? This is relevant because the PCE price index, which is constructed by the BLS, is something that is not measured, sorry, by the BA, is something that is not measured directly by the BA. So rather the BA, what they do, they construct each PCE price index by looking for a corresponding CPI or a corresponding PPI, mostly are CPI. And where they don't have a CPI or a PPI, they impute the price, meaning that they estimate somehow these prices. Okay. And what happens is that some disaggregated PCE prices are constructed out of the same sources. Here I have an example, which is domestic autos and foreign autos, which are two different categories in the PCE price decomposition. But in the CPI ones, there is just the CPI of new cars. So if you take these two PCE prices, they are the same. And these create a very big problem when you estimate a dynamic factor model. And so in order to preserve the structure of the PCE price index, and therefore being able to do the aggregation, I had to go through each data source and aggregate aggregate them according to the data source of each disaggregated prices. Moving to the results at this point, as I said, what I'll do a decomposition of the month-over-month inflation. So here is the black line is core PCE prices. The red bars are the common component, and the yellow bars are the idiosyncratic components. There are a number of the model is capable of capturing a number of very well famous events in which idiosyncratic movements were particularly relevant, and I mentioned a couple of those in the introduction. So for example, here I have circled in blue the period between 2014 and 2015, where the medical prices were low, and they were low simply because of the implementation of the Affordable Care Act, so the Obamacare. So inflation went down, driven by medical prices, but medical prices were not really going down for an economic phenomenon. It was an administrative issue. And another example is this dot here is the March 2017 reading of the wireless telephone services. There, the story essentially was that all the carriers switched to unlimited data plans. And so the BLS had to adjust the prices, and this determined a huge drop in the core inflation index. So if we zoom into the last 2 years of my data set, so 2018 and 2019, there are also a number of interesting and funny stories. Like, for example, this one, August 2018, inflation, core inflation was low. Why it was low? Well, the CPI for dental services recorded the lowest ever reading that month. So in this case, it was relatively easy to spot it. The beginning of 2019 were non-market prices, where non-market prices are those that are, in general are imputed by the BLS. Okay, so this is the year-over-year inflation. And basically, I want to zoom on the last part from the Great Recession onwards. And you see here the black line is core PCE prices, and the red line is common core inflation, so the common component. If you look after 2010, core PCE prices fluctuated approximately between 1
Matteo,
and 2. Yes.
5 minutes remaining. Yeah.
Okay. Between 1 and 2, 1 and 2%, while common core inflation fluctuated between 1 and 6 and 1.8. So meaning that essentially most of the fluctuation in the last 10 years were of an idiosyncratic nature. So the paper goes on with a number of exercises. Essentially, I show that in terms of data revision, this model does very well. It revises way less than core PCE prices, and it's not subject to residual seasonality, and also that is linked to economic slack, so to the unemployment rate, through a very flat Phillips curve, but this Phillips curve is clearly identified. So the coefficient is highly statistically significant. So I won't cover all this. I want briefly, in the last few minutes that I have, to talk about essentially the COVID effect. So basically what I show is that once you include COVID into the sample, these had a great effect on the estimation of the co-movement. So the red line here is the estimate of common core inflation without COVID, and the blue line is with COVID. So the red line essentially is estimating up to February 2020, and the blue line is estimating up to April 2020. So just adding 2 observations generates this huge change, and this huge change is like 10 times the average change in the real-time exercise. So I exploit this kind of in a diff and diff flavor to identify the COVID effect, and essentially now I'll go over a few slides. Here I augmented the composition to include also the COVID effect and 2020. And so here the green bars are is the COVID effect. And you see that in the first 3 below 0 green bars are March, April, and May of 2020, in which COVID had really a huge negative effect, and then throughout the summer, a positive effect. And if you aggregate this through time to construct month-over-month inflation, this is the graph, and the red, the green area is the COVID effect. And at the end of the sample, which is December 2020, I estimate that approximately the COVID effect shaved off 0.2 of a percentage point in 2020 to core PCE price inflation. If I'm not wrong, I'm really running out of time. And so here I have I had a few slides on economic slack, and I told you what this was about. Essentially is this line that is highlighted in yellow, unemployment gap. So very flat coefficient of the Phillips curve, but highly statistically significant. And therefore, the conclusion of this analysis is that the flattening of the Phillips curve is really a macroeconomic result of macroeconomic forces and not of some measurement error or noise in the data. I see that it's 4:21, which is, I believe, 1 or 2 minutes over my time. And so basically,
you have 1.5 minutes. Okay. You have time.
I have time. So basically, so these are my conclusions. So the idea is to have a data-driven model that can decompose inflation changes into common and idiosyncratic. And I do that using this very nice large data set of disaggregated PCA prices and by estimating a dynamic factor model. And the main result is that between 2010 and 2019, most of the fluctuation in core PCE prices were really of an idiosyncratic nature, so very low effect of macroeconomic forces. But that COVID had a very important and negative effect in 2020. And then also there is the result that I just mentioned about the flattening of the Phillips curve. And as I said before, that common core inflation does not suffer of residual seasonality and revises way less than core PCE prices inflation in real time. That's it. Thank you. I'm happy to answer any questions.
Thank you, Matteo.
Yes.
We have 2 questions right now. The first one is by Simon Shang and then James Mitchell. So let's, can we please unmute Simon Shang?
Yes, my question is, look, your estimation assumes stationarity, right?
Yes.
So how can you incorporate the large and fast-moving structural breaks, say COVID, into your estimation? Or generally, so can your model incorporate and address this very large shocks, the so-called breaks, structural break?
Here, what I saw is that if you estimate the model included COVID, so what happened during COVID, that many prices moved in the same directions, okay, generating a big fluctuation in core PCE prices. Now, in order for the model to fit that part of the sample, it's gonna take a lot of signal from a number of prices that normally are idiosyncratic. I can give you a few examples. One is the price of clothes, so apparel prices, or the prices of airfares. These normally are very idiosyncratic prices. And instead, as soon as you put COVID into the picture, you have this will distort your estimates. And playing on this distortion, basically what I do, I estimate the model. So I create the common core inflation, the red line is constructed by estimating the parameters up to before COVID and then running the filter to close to estimate for the rest of the sample. And then I estimate again the model allowing the parameter to change with COVID. And then as a difference, I estimate the first, the COVID effect. But it's true, the COVID per se screws pretty heavily the model. And in fact, going forward, one has to do some intervention analysis to keep estimating the model without having this very huge event to contaminate your estimation. But let me tell you one thing, This is the only event throughout the sample that created a very big change on the parameters.
I agree. Thank you.
Yeah.
Can we please unmute James Mitchell?
Hi, Matteo. It's James Mitchell here.
Hi, James.
Hi, I'm from the Cleveland Fed now. I've changed jobs since we last.
No way.
Anyway, we can talk about that another day. So my question, in many ways, follows on from Simon's in thinking about the effects of breaks, of shocks, of uncertainties. I was wondering, can you tell us anything about the uncertainty around your point estimates of core inflation? Indeed, can your dynamic factor model, be used to produce confidence intervals of that sort around these estimates of core inflation? Because I can imagine, it's those uncertainties that could be particularly important, including right now, of course. Thank you.
So yes, so I tried to do that, and I tried to do that using bootstrap method. I used a similar technique in another paper, and in which we estimated the output gap, and over there it works very well. In this case, I get huge confidence bands. Now, why is that? And the reason is that the main thing that I realized working on this is that the common signal in the data is very weak. So if you look at a standard Stock and Watson data set of macroeconomic data, you have a very strong common signal. You have a lot of commonality. Here on prices, you don't. And this is actually per se a result, and also a result that unveil other researchers, which is why I haven't stressed it out that much. But essentially, disaggregated prices are very, very much idiosyncratic driven. And therefore, I haven't really been able to construct a meaningful confidence band. I mean, you have a confidence band with I don't know, a range of 1 percentage points, and then they are useless at that point. So that's the honest answer.
Okay, thank you. That's very interesting as well.
So theoretically, I have the confidence band for each disaggregated prices, but I haven't thought yet how, once I have the confidence band of each the disaggregated prices, I can what happens when you do the weighted average.
Yeah, I mean, you'd sort of hope, wouldn't you, that those uncertainty estimates around the disaggregate, many of them might cancel out when constructing the confidence interval around the aggregate, as it were, and thereby the uncertainty around the aggregate might be sort of more contained than around many of the disaggregates, such as energy prices and things.
Yeah. But I mean, essentially, there is a lot of noise. So that's a very complicated signal extraction problem because the signal is weak.
Yeah. Agree. Thank you. Very interesting.
Yeah.
Thank you.
Thanks.
Okay. We have a time for one more question. Okay, I think that's it. Thank you so much, Matteo.
Thank you.
I would request you to please unshare your screen so Zoe can then share.
All right.
Okay, can you all see my screen?
Yes.
Thank you very much. And thank you everyone for joining this session today. And I'd also like to thank the organizers for including our paper in the program. So I'm Zoe Xie, a senior policy analyst at the George Washington University Regulatory Studies Center. And this is a joint work with Tara Sinclair. So first of all, why should we care about regulation? So let's start looking at a couple of newspaper quotes first. Last year, the Washington Post reported that owners of medical dispensaries invested in new technologies for drive-through windows, but it could not legally open without a change in statewide regulations. And also last year during the election week, according to the Wall Street Journal, US stocks surged as investors cheered the prospect of curbs on new regulations under a split Congress. So like these news articles highlighted, many economic activities are subject to government regulations. So as you know, regulation can cover a wide range of issues such as the environment, transportation, consumer safety and health. And the regulation can also generate substantial economic effects in both direct and indirect ways. So therefore, in this study, we examined the macroeconomic effects of sentiment and uncertainty about regulation in the United States. Specifically, using computational text analysis of multiple US newspapers, we constructed two sets of text-based measures. One is a regulatory sentiment measure that assesses the positive and negative sentiment around regulation in the news. And the second is a regulatory uncertainty measure assessing the level of uncertainty about regulation in the news. And we track regulatory sentiment and uncertainty at a monthly frequency from 1985 to 2020, both in aggregate and for 15 individual regulatory policy areas. And we then used VAR to examine how macroeconomic indicators respond to sentiment and uncertainty shocks about regulation. So as you know, it's usually hard to draw any causal conclusions from VAR, but the impulse response functions suggest some interesting dynamic relationships in our study. So just give you a preview of our key findings. Our analysis suggests that a negative shock to regulatory sentiment is associated with large persistent drops in future output and employment. On the other hand, a regulatory uncertainty shock reduces output and employment temporarily. And using our categorical measures, we also found that economic outcomes are particularly sensitive to sentiment and the uncertainty around certain policy areas, such as transportation, general business and trade, and labor regulations. Our study connects to three bodies of literature. First, it connects to the literature of economic sentiment and policy uncertainty. So in both areas, text-based measures have gained increasing attention during recent years. Those include the high-frequency news-based measures, such as the Economic Sentiment Index of Shapiro et al. 2020, and the Economic Policy Uncertainty Index of Baker et al. 2016. Many studies have found that measures of economic sentiment and policy uncertainty reveal information about current and future economic activity. So similarly, in this paper, we argue that news-based measures of sentiment and uncertainty about regulation can also provide important information for understanding economic effects of regulation. So in that sense, our study also connects to the literature studying the aggregate economic effects of regulation. This literature has mostly focused on the volume or the stringency of regulation. So our study focuses on different attributes of regulation and presents a new direction in this research. So as I mentioned, we use newspaper data to construct our measures. And our initial news corpus includes the full text of over 800,000 news articles from 7 US newspapers. And those articles contain the keywords starting with regulate or deregulate, such as deregulation, regulation, and regulator. And the articles were published between January 1985 to August 2020, so as listed in this table. And from the initial corpus, we removed the articles with the identical content to a previous article. Among the remaining unique articles, we then identified nearly 500,000 articles that contain regulation-related content. So how did we identify the regulation-related content? So as I mentioned, the articles in the initial corpus all contain the keywords regulation or its variations. But a problem with this corpus is that it also includes some false positives. Here are two examples that show sentences both containing the word regulation. We would want to identify the cases like the one on the left here, which refers to federal regulation on financial markets. But the initial corpus also include cases like the one on the right here, which refers to a sport game. So therefore, a simple keyword search could not give us a very clean corpus related to regulation. To solve that issue, we assessed the context in which the word regulation or its variations are mentioned. And we did that by defining a dictionary of regulatory noun trunks. You can consider a noun trunk as a subset of noun phrases. Specifically, we first identified noun trunks from all unique titles of all rules considered by federal agencies from 1995 to 2019. For example, this EPA rule contains 4 noun trunks: test procedure, analysis, trace metal, and Clean Water Act. And we only keep the noun trunks with 2 or more tokens because a single token noun trunk like analysis here is too broad to suggest any relevance to regulation. And we iterate this process over all unique rule titles and eventually generated a large set of unique and token noun trunks. As a second step, we then searched the noun trunks in the initial news corpus to identify specific sections related to regulation in each article. We define a section as a sentence that contains the keyword regulation or its variation and its neighbor sentences. And if a section contains 1 or more noun trunks from rule titles, we then define it as a regulatory section. So here is an example of a regulatory section. In this section, animal drug, regulatory barrier, and human research are all noun trunks from rule titles. And in the case where an article has multiple regulatory sentences, all those sentences and their neighbor sentences compose the regulatory section of the article. And finally, after some human checking and correction of the noun trunks, we ended up with a dictionary of over 10,000 regulatory noun trunks that occurred in nearly 500,000 news articles. So using the identified regulation-related content, we can see how news attention to regulation has changed over time. So this figure shows regulation-related news articles adjusted for the total number of articles published in each newspaper in each month. Clearly, there is an overall increasing trend in news attention since 1996. And as a means of verifying the validity of the index, we see that large spikes and jumps in the index capture important historical events, such as the Lehman Brothers bankruptcy, Obamacare, and the Dodd-Frank Act. So overall, the increasing trend suggests that regulatory policy has become an increasingly popular topic in the news. We then examine the content by assessing the sentiment and uncertainty expressed in the relevant news. Specifically, we use a lexicon-based, or you can say a dictionary-based sentiment analysis approach. This approach relies on predefined dictionaries of opinionated words. We use the Lagrange and the McDonough dictionary in our baseline analysis. The LM dictionary includes lists of positive and negative words, as well as a list of words that express uncertainty and imprecision. Based on how many positive and negative words occur in the regulatory section of a news article, we can calculate the sentiment score of each article. And because the sentiment score can be largely affected by the balance of positive and negative words defined in the dictionary, we also used 2 other alternative dictionaries to assess sentiment for comparison. Those include the Harvard GI Dictionary and the LSD. So we'll see the results using different dictionaries later. And the uncertainty score for an article is simply the proportion of the uncertainty words occurred in the regulatory section. To construct indexes that show changes in sentiment or uncertainty over time, we followed Shapiro et al. To use a fixed effects regression. So on the left-hand side here, we have the estimated sentiment or uncertainty score for each article. On the right-hand side, we have year-month fixed effects and newspaper fixed effects. The monthly sentiment or uncertainty index is the estimated coefficients on the year-month fixed effects from this regression. And the newspaper fixed effects can address the potential concern of ideological divergence across different news sources. And this figure shows the standardized sentiment indexes estimated using the 3 different dictionaries. As you can see, there are some variations in the 3 indexes, but they generally suggest very similar patterns in sentiment about regulation over time. The correlations between the indexes are also quite high, with the LM and the LSD dictionary, the LM and LSD indexes correlated at 0.8. The first principal component of the 3 sentiment indexes explains about 80% of the variance. And this figure shows the regulatory uncertainty index. In particular, we see more spikes in regulatory uncertainty during recent years, including the months around the 2016 presidential election and the coronavirus outbreak last year. We then use VAR to estimate how measures of economic activity, especially output and employment, respond to regulatory sentiment or uncertainty shocks. Our VAR setup follows Baker and et al. 2016. We estimate the impulse responses to a 1 standard deviation negative sentiment shock or a 1 standard deviation upward uncertainty shock, respectively. We orthogonalize the shocks using the Cholesky decomposition with our sentiment or uncertainty index as the first in the causal ordering, followed by standard macroeconomic indicators. And we included 3 legs of all the variables in the VAR. And in addition to the baseline analysis, we also did a series of robustness checks, including those done by Baker et al. In addition, we also included the economic sentiment index of Shapiro et al. 2020 and the EPU index of Baker et al. 2016, just to see whether our measures of sentiment and uncertainty about regulation are picking up any effects of the general economic sentiment or policy uncertainty in the news. So here are the impulse response functions. From the left-hand side figures, we see that a negative sentiment shock reduces future industrial production and employment. The effects on industrial production are significant at the 10% level between 6 and 15 months after the shock, and reached a maximum drop of 0.35%. The effects on employment are more persistent, lasting up to 24 months after the shock, and the maximum estimated drop is about 0.2%. Comparatively, on the right-hand side, a regulatory uncertainty shock only leads to a moderate drop in industrial production and employment, and the effects vanish very quickly in a couple of months after the shock. And these impulse response patterns are robust to the modifications of the specification I just mentioned, but for the sake of time, I'm not going to show the output here. To further explore
Zoe,
what types of regulatory policy drive the connection between, yes. Okay, thank you. So to further explore what types of regulatory policy drive the connection between regulation and macroeconomic outcomes, we also constructed categorical indexes for different regulatory policy areas. We classified regulation-based articles in our sample by using the regulatory non-trunks I just described. So as I mentioned, the regulatory non-trunks were extracted from rule titles, and we know that rules were issued by federal agencies with specific regulatory authorities. So we defined regulatory areas according to the authority of the associated agency. So let's look at a simple example here. So in this regulatory section, we have 4 regulatory non-trunks, including seatbelt, federal regulation, airbag, and seatbelt. And all the rules in which the terms airbag and seatbelt appear were issued by the Department of Transportation, which is clearly transportation regulation. And the term federal regulation appeared in many rule titles. So we just dropped those non-trunks when we categorize the articles because it would create a lot of noises. So in this case, the area associated with the airbag and the seat belt determines the area of this article. And in longer regulatory sections, we define the dominant area as the most common area across all the non-trunks in the regulatory section. As a result, we categorized the regulation-related articles into 15 regulatory areas. As you can see, finance and banking is the area that has drawn the most news attention. We then created categorical indexes of regulatory sentiment and uncertainty for each area using the same approach we used for the aggregate indexes. And from the impulse response functions, we find particularly strong linkage between sentiment and uncertainty around certain regulatory areas and future economic outcomes. For example, we observed a statistically significant drop in future output in response to a regulatory sentiment shock in the areas of transportation, environment and natural resources, finance and banking, and general business and trade. In particular, the effects of sentiment shocks to transportation regulation and the general business and the trade regulation are more persistent. So the bottom 4 figures shows the employment responses. We also observe persistent employment effects around transportation and the general business and trade regulations. As I discussed earlier, we did not find persistent effects of a shock to the aggregate regulatory uncertainty measure. But when we look at individual areas, we observe measurable and persistent drops in both output and employment after uncertainty shocks around transportation regulation and the labor and workplace regulations. In particular, the output effects of regulatory uncertainty around labor and workplace regulation is very persistent, remaining significant up to 55 months after the shock. So let me conclude our study. We constructed news-based measures of regulatory sentiment and uncertainty, and our analysis suggests that negative news about regulation may lead to persistent drops in future output and employment, and increased policy uncertainty overall has transitory effects. Also, using our categorical indexes, we find that economic outcomes are particularly sensitive to sentiment and uncertainty around certain regulatory policy areas. Those include sentiment around transportation and general business and trade regulations, as well as uncertainty around transportation and the labor and workplace regulations. And that's all. Happy to answer any questions.
Thanks, Zoe. Any questions, please type onto the QA window. Okay, we have a question from James Mitchell. So please, can he be unmuted?
Hi, it's James Mitchell from the Cleveland Fed. Very interesting paper. So I had a couple of sort of questions, but it may be I maybe missed what some of the details of what you're doing. So apologies if you did speak to these already. Firstly, I wondered, in doing your textual analysis, whether you also searched for synonyms of regulation. For example, maybe the newspaper talks about red tape or bureaucracy instead of rather directly using regulation or deregulation. And secondly, in your VAR analysis, which I thought was very interesting, I wondered, did you control for more traditional, such as the EPU measure of uncertainty that you spoke about? Did you control for those traditional measures of uncertainty in your VAR analysis? In other words, I wondered, is your regulatory uncertainty proxying in some sense or not for these more traditional, more aggregated measures of uncertainty? Thank you.
Mm-hmm. Yeah, thank you for the questions. So to the first question, our initial corpus only contains the articles that mention the word regulation or deregulation and its variations. But when we further refine our corpus related to regulation, we used the non-trunks from all the rule titles. So if the terms you mentioned, like red tape and bureaucracy, were used in those rule titles, we included those terms when we identified articles related to regulation. So
okay,
we did
good.
not, we did not subjectively determine the list of terms because we want the computer to automatically identify the terms based on the titles of federal regulations. And to the second question, yes, we in our robustness checks, we also controlled for one, the economic policy uncertainty from Baker, Bloom, and Davis 2016, and the second, we also controlled for the general economic sentiment index constructed by Shapiro et al. 2020. So and when we did that, all the impulse response functions did not change substantially. So yeah, I think as you just mentioned, we were just checking if our regulatory indexes were picking up any information in the news about the general economic sentiment or policy uncertainty, and our robustness checks show that it did not.
Okay, that's very, very interesting and very good. So yeah, thank you very much.
No problem.
We have another question by Kareem Tuscuglo. So please, can he be unmuted?
Hello. Thank you very much for the nice presentation. My question is about these news-based or uncertainty measures in general. So are they net of the aggregate uncertainty, like EPU, for instance? Because when I look at your IRFs, I see that at least according to my own bias prior, the magnitude seems to be high. And if that's how much IP is responding to regulatory uncertainty, and then we have other measures from the monetary policy uncertainty, fiscal policy uncertainty, if we add them up, then the effect is becoming huge. So does your uncertainty measure contain maybe the aggregate uncertainty somehow, and that's why the magnitudes are so large? And if that's the case, maybe what happens if you regress your uncertainty on, let's say, the EPU, and then you take the residuals, and that's going to be sort of the orthogonal part, maybe literally regulatory specific, and then use this in your VARs. Thank you.
Mm-hmm. Mm-hmm. Yeah, thank you for the question and the suggestion. Yeah, I agree. I think there might be some overlaps between the regulatory uncertainty and the general policy or macroeconomic uncertainty here. But since in our robustness check, we did not see the effects of a regulatory uncertainty shock still remains after we control for the general economic policy uncertainty. So I think there is still unique information provided by the regulatory uncertainty measure here. But I think your idea to regress our measure on the economic policy uncertainty and take the residual is very interesting, and I will try that. Thank you.
Thank you, Gina. Good luck.
Okay, thank you very much, Zoe Shir. Could you please unshare your screen? Thank you.
Okay, so I would say that we can move to the final presentation by Said Zaman on real-time density nowcast of US inflation. Said, if you can share your screen.
Thank you, Matteo.
Yeah. The floor is yours, and I will warn you when you have 5 minutes left.
Okay, great. Thank you so much, Matteo, and thanks everybody for attending my session. Just one, before I proceed, Matteo, can you hear me? Can you see my slides?
Yes, perfect and clear.
Okay, great. This is joint work with my colleague, Edward Nortek at the Cleveland Fed. And the usual disclaimer applies that these views are ours and not necessarily those of the Cleveland Fed or the Federal Reserve Board and the Federal Reserve System. Okay. Okay, so inflation developments are important for a variety of economic agents, including central banks and public. And so naturally, there is interest in inflation nowcasting process. And research has also shown that multi-horizon inflation point forecast accuracy could be improved by conditioning these quarterly macro models with high quality inflation nowcast. So motivated by these facts, my colleague, in recent past, my colleague Ed and I developed a simple mixed frequency model to nowcast both the headline and core inflation. And our focus of that paper was on point nowcasting. And we donated that model as a deterministic model switching, which I will talk in a bit about why we donate with that terminology. But in that paper, we documented like highly competitive nowcasting properties of that model compared to the outside sources such as the Blue Chip, survey of professional forecasters, and also the Teal book from the Federal Reserve Board. And just to quickly market our previous stuff, the estimates, the nowcast estimates from our that model are updated daily at the Cleveland Fed website, all the way going back to 2014. And so what about the density estimates, density nowcast of inflation? So in the recent years, there has been increasing interest in like density nowcast of macro variables due to the increasing like recognition of the value added that the density estimates bring to the table. They actually help with balance of risk assessment around the point estimates. And again, research has also shown that there are gains in multi-horizon density forecast accuracy by conditioning the multivariate models such as VAR and DSG models with both the nowcast mean and nowcast variance. And hence it allows for a more reliable risk assessment of probability events such as risk of recession or the risk or the probability of deflation over the next X or Y quarters or so. So but most of the recent work on density nowcasting has mainly focused on real variables such as GDP. But what this paper does is it focuses on the density nowcast of US inflation. The goal of this paper is to consider approaches based on model and density combinations to generate density nowcast of inflation that updates as information accumulates over the course of a month or quarter. So why model combination? This is because the characterization of uncertainty from a single model, single possibly misspecified model could be restrictive. And by combining evidence from a range of models could lead to a very flexible density, which would like to be more accurate. And also in addition, it's going to be more likely robust to structural instabilities. But that being said, this increased flexibility may not necessarily translate into improved accuracy. So at the end, it is an empirical question. So what we do in this paper is develop a model and density combination framework to produce density and point nowcast of inflation at a daily frequency. We consider 3 classes of mixed frequency models that research has shown to do quite well in accurately nowcasting the point nowcast of of both headline and core inflation. Those three classes of models are the MIDAS dynamic factor model and the DMS from our earlier work. So inspired by the previous research by the Nowcasting economist in density nowcasting GDP, we implemented two-step or two-stage procedure for combination. So in the first stage, we generate density nowcast from several model specification within each of these three mixed frequency model classes. And then we combine them within each of these mixed frequency model classes. And that gives us three separate estimates of density nowcast corresponding to three mixed frequency models. And then in the second stage, we combine these three estimates to form a grand combination. And why this two-stage process? Because there has been evidence documented in the literature that by doing so, by following this two-stage procedure, you can directly account for uncertainties and instabilities about model specification within each of the model classes. In doing the aggregation, we implement a novel flexible treatment that dynamically aggregates these individual candidate density nowcasts. I would also emphasize that even though density estimates are useful, but the point estimates, the point forecasts are of first order importance. So for our density estimates to be taken credibly, we desire that the accuracy of the implied point nowcast from the combined densities should be at least as accurate as the accuracy of the point nowcast from our previous work. So we consider several strategies in how best to combine densities in the context of US inflation. And we then examine the real-time accuracy of all these various approaches, accuracy of the combined density nowcast based on these various approaches. And hence our paper could be seen as a comprehensive examination of combination methods for US inflation nowcasting. A byproduct of our research is this head-to-head nowcasting horse race, comparing these traditional weighting schemes with those proposed more recently. So what we find is that combining densities generally helps improve density accuracy. But importantly, it matters how you combine them. That is, not all combination methods that we considered improve accuracy. What we find is that the grand combination based on this flexible aggregation strategy and the log score weighting scheme generates well-calibrated densities and is among the most accurate for both density and point nowcast accuracy. We also find that the accuracy of the implied point nowcast from this grand combination matches the accuracy from our baseline model from earlier research. We also find evidence of time-varying uncertainty, skewness, and kurtosis in the predictive densities of all the inflation measures we consider, suggesting that symmetries and fat tails are empirical feature of inflation data. And lastly, we also document our competitive nowcasting properties compared to the survey of professional forecasters. Especially, we show that our nowcasts are substantially more accurate in the case of headline inflation, and they are competitive in the case of core inflation. So very quickly, the outline I'm going to go is I will very, very briefly talk about related research. We'll talk about very quickly about the mixed frequency models that we use. Then I will talk about this combination methods, that is the aggregational functional form to combine the candidate densities. I will then talk about the weighting schemes, like the mechanisms through which we like the strategies that we'll use to come up with the weights for the individual densities. I will talk about the design of the density evaluation exercise. I will talk about the results and then conclude. Okay, so this paper lies in the intersection of three growing areas of nowcasting, mixed frequency models, and density combinations. In the interest of time, I'm going to say this much only. But in the paper, we cite many of the people, including some who are in the audience right now, in particular James Mitchell's work. Okay, so So when it comes to inflation, it has been shown that parsimonious approaches tend to dominate the more sophisticated approaches. So accordingly, in this paper, we entertain those models, mixed frequency models that are all parsimonious formulations, and they in particular relate aggregate inflation either to its disaggregates or to indicators that have been shown to have some influence in predicting inflation. So I'm going to just give a very in the interest of time, I'm just going to be giving a very top overview of these three model classes. So the first one is the DMS model class, which is based on our earlier work. It has three features. First, it uses a small set of data series to inform the Nowcast estimates of monthly and quarterly inflation. The second is that it combines simple univariate and multivariate regression techniques estimated over short rolling windows. And third, it imposes time varying weights on the disaggregate and aggregate variables in nowcasting the aggregate that deterministically change based on the available information set at a point in time. Hence, it takes advantage of this high frequency information flow over the course of a month or quarter, and hence we denote it as a deterministic model switching. It uses disaggregate information for the aggregate only when the information is available and deemed to be informative. So in this model, high frequency data affect the monthly nowcast, which are then aggregated to form the quarterly nowcast. Density nowcasts are basically generated using a parametric block wild bootstrap, which is slightly more accurate than the standard residual based bootstrapping procedure. This is because the wild bootstrap procedure takes into account autocorrelation and heteroscedasticity in the errors. Moving on to the second model class, it's a mixed data sampling MIDAS models. Like we use this MIDAS model with leads in the spirit of Monteforto and Moratti, who focused on point nowcasting euro area inflation. These MIDAS models are reduced form regressions that basically relates different processes that are sampled at different frequencies. And like a little over a decade ago, Anna Galvao, in joint with Michael Clements, successfully applied these models in forecasting macro variables. And since then, they are commonly used to nowcast and forecast macro variables. So in our paper, the MIDAS we are using, the daily oil prices and the weekly gasoline prices act as high frequency leads. It is estimated with nonlinear least squares, and the density nowcasts are computed by drawing errors from a normal distribution whose standard deviation is set equal to the standard deviation of the past residuals. Recent research has shown that this approach is just slightly inferior to the block wild bootstrap, but it has huge computational advantage. Therefore we adopted for our paper. The third model is a dynamic factor model, which is a very popular model in like a modeling framework to nowcast macro variables. And the model that we use is exactly the model developed by Moduno, who uses it to nowcast aggregate US inflation. I would say that compared to the MIDAS and DMS model, the DFM uses a lot more data in nowcasting the inflation. It combines data at the monthly, weekly, and daily frequencies into a business day frequency factor model, where the missing observations are cast in a state space representation. The unobserved daily factors aggregate to weekly and monthly factors, which in turn then inform nowcast and forecast of the monthly variables and then quarterly variables. The density nowcasts are computed using a standard parametric bootstrapping procedure for factor models that takes into account parameter, shock, and factor uncertainty. Okay, so for all these three mixed frequency model classes, there is a considerable uncertainty regarding the specification. So for example, should it be estimated over a rolling sample? And if rolling sample, then what should be the length of the rolling window? What about the number, how many factors to use, right? And then how many lags to use? So accordingly, we account for this model specification by considering many different specifications within each of these model classes. And this table here provides, gives you a sense of the dimensions along which you form different specifications. So we consider about 132 model specifications distributed unequally across the three model classes. Okay, so when combining densities, there are two questions that needs to be answered. First is that the functional form for aggregation, and the other one is the weighting scheme. So beginning with the functional form for aggregation, we considered three. And the first one is the linear pool, which is the most popular one, and it's the most intuitive one. It is simply a linear combination of m different densities. For here on the left, as you can see, in the equation, the left-hand side is the combined predictive density at point in time tau within the month t for forecast horizon h. And here m is the number of models. Here you can think about as the number of candidate densities. And in the rightmost term is the density forecast from model I conditional on information set I tau ti, which can differ across models. And the weights at any point time tau are potentially time varying, and they are all non-negative and should sum to 1. An advantage of this linear opinion pool is that if all the individual densities are normally distributed with different mean and variances, the combined density would be a mixture normal. And so hence it can entertain skewness and kurtosis, which is like if the true unobserved density is not normal, then this is a desirable feature. The second one is the logarithmic opinion pool. It is the second most widely used aggregation function, and it is simply a geometric weighted average. Geometric weighted average. And one key property of this pool operator is that, like, if the individual candidate densities are all normally distributed, then this combined density would also be normally distributed. That is, it maintains the symmetry of the individual component densities. One undesirable feature of this operator is that that the combined density would assign a 0 probability mass to a region if a single candidate density says that it should be assigned a 0 probability. So this contributes to its reduced dispersion. And in general, log pool is less dispersed than linear pool. Okay, and the third one is this novel flexible aggregation method. Basically, what it does is it does in a flexible way. It basically uses the previous two functional forms in a more data-dependent way. What I mean by that is that instead of enforcing a particular functional form at the outset, what it does is it lets the data tell us which one at any given point in time does it favor. So specifically, at any point time tau, when nowcasting for target month t, this approach is going to look in the past and see at that point in time, like which of the functional form was preferred. So this approach has an advantage of potentially allowing this switching at different points in time during the course of the month. For example, earlier in the month when there is a higher uncertainty because you have a lot less data to do nowcast, you have a lot more uncertainty around the point estimate, like the wider bands in density. And you would intuitively think that the linear opinion pool, which is more flexible, may be preferred. But as later down in the month, as you have more information and you have more dispersed densities, you would think that the log opinion pool would be preferable. So it allows this flexibility. Okay, so moving on to the second one is the weighting schemes. We consider 5 in total. The first one is a very simple 5 in total, ranging from the equal weights to the optimal to a scheme based on optimal optimization of some loss function. So the first one is the equal weights criteria. Like each density gets equal weights. The second one, second and third are based on past predictive performance measured using the most commonly used scoring metrics in density for the density forecast. It's the log score and the CRPS. And the last two are based on optimizing a loss function. The first one is maximizing the log score of the combined density, and the last one is based on Gannick's approach, in which it maximizes the calibration fit. In this presentation, for the remaining part of the presentation, I'm going to focus on the combination based on the log score weighting scheme and the flexible aggregation strategy. This is because it yields well-calibrated densities, and also it is among the most accurate when it comes to based on the relative accuracy of log score and CRPS. I would also note here that the GANX approach, which is based on optimizing the calibration fit, as one would expect, generates the best calibrated densities, but it is inferior in some ways when it's compared based when you assess the densities on the relative accuracy of log score and CRPS. We also adopt this approach because the point forecast accuracy is among the most accurate, and it matches the accuracy of the best performing model from our earlier work. I would also note here the results are identical to using if we would have used a linear opinion pool for aggregation at the outset. And this is because the flexible aggregation strategy almost always selects linear opinion pool over the logarithmic pool. Okay, and so we evaluate the density, we assess the evaluation of our density estimates by range of metrics to evaluate both the absolute accuracy and the relative forecast accuracy. So absolute forecast accuracy basically tests the calibration fit of your density estimates, and the PIT, probability integral transforms, are the most widely used metric to assess the calibration fit. And we actually do both the visual assessment and formal statistical tests. And we also assess our calibration using the interval forecast. We do a lot of results, and they are in the paper. For this presentation, I'm going to focus on the relative forecast accuracy, which are based on the log score and continuous rank probability score. And our evaluation sample is the past 15 years of data from 2000 to 2015. This is to facilitate comparison between this paper and our earlier work.
Said, you have a little bit less than 5.
Okay, great, thanks. So nowcasting, so inflation rates for the paper, we do month-to-month inflation rate, 12-month % change, and quarterly. So 12-month. So this presentation going to focus on the 12-month % change. That is more gets usually more like a wide press coverage, because the Federal Reserve's target is framed in terms of 12-month % change. And I would also quickly mention quarterly estimates are important, because for quarterly macro models, you augment them by basically providing quarterly nowcast. I illustrate the performance at a set of 6 representative nowcasting dates that takes into account the real-time data flow. For truth, we use a third monthly estimate of CPI and PCE prices. We do comparison among the DMS specification, MIDAS, DFM, and the grand combination. In interest of time, I will move forward, but there are these 6 cases at 6 different points in time within the month where we evaluate our density, we produce and evaluate our density nowcast. Okay, moving on to the results. So beginning here with the comparison of the grand combinations. So here there are these 4 panels corresponding to 4 different inflation measures. And on the y-axis is the CRPS score. Just to remind you guys that lower is better, meaning more accurate. And then in each panel, there are these 5 plots corresponding to 5 different combinations. All these combinations are based on the flexible aggregation method. So basically, this comparison boils down to 5 different weighting schemes. As you can see here, the weighting scheme based on log score generates the most accurate, is among the most accurate in producing the density nowcast. And the other feature you can see is that on the x-axis, moving from case 1 to case 6 suggests that there is more high frequency information. So as you get more data, in general, you would see that the accuracy increases. And this is a corresponding table of the accuracy of the implied point nowcast. Again, you can see the log score weighting scheme generates the most accurate point nowcast as well, just like was the case for the density nowcast. Now moving on to this comparison based on the grand combination and its underlying 3 combinations, like the DMS class, DFM, and MIDAS. So here you could see the grand combination and the DMS combination are among the best performing. In the case of core, all of them are competitive, but for the case of headline, grand and DMS are the best performing. Moving on to the point nowcasting performance, here what I do is I show the GRAND and DMS. That is the ones like from this chart, the most accurate, DMS and GRAND. And then I also plot to facilitate comparison the point forecast accuracy from our earlier work. As you can see, that GRAND combination is among the most accurate, and it matches the accuracy from our previous baseline model, from our baseline model from the previous work. But we can see that the GRAND is more accurate in the case of core PCE compared to our previous work. Okay, lastly, I'm going to quickly show this comparison with the survey of professional forecasters. So, so it has been well known that in terms of point nowcast and forecast accuracy, SPF, like the survey forecast, are a pretty good benchmark. This is because of the flexibility of the respondents to adjust their estimates in a more rapid fashion in response to high frequency and judgment. High frequency data and the judgment. However, when it comes to the density estimates, research has shown that their raw density estimates are like inferior and of poor quality. So that
you
being
have
said,
1 minute.
Okay, thank you. But that being said, the density nowcast, so Michael Clements and others have shown that if we estimate the density nowcast based on a simple approach that uses past historical errors, that is a pretty good benchmark. Specifically, what I'm saying is that if you construct the densities using a normal distribution with the mean set equal to the median SPF point nowcast and the variance set to match the variance of the past historical errors of this SPF median nowcast over a 4-year rolling window, that is a pretty good benchmark. So then we compare with that benchmark. So here is this slide showing the comparison. The top panel is the point nowcast comparison, and the bottom panel is the density nowcast comparison. The first two rows, the first row correspond to the RMSE from the GRAND, and the second row is from the SPF. As you could see, in the case of headline, like CPI and PC inflation, our combined densities from the GRAND is quite accurate compared to the SPF, and the gains are statistically significant. In the case of core, it's competitive. The same is the case for the density nowcast comparison. Okay, so I would now summarize by saying that in this paper, we explore the production and accuracy of the density nowcast for US inflation measures using combination derived from 3 classes of mixed frequency models. We do a comprehensive empirical examination which reveals that for density accuracy, it matters how you combine the density estimates, and we find that the GRAND combination, based on the flexible aggregation strategy and log score weighting scheme, generates well-calibrated densities and is among the most accurate for both density and point accuracy. And we also show that the accuracy of the implied point nowcast from the GRAND combination matches the accuracy of the baseline model from earlier work. Lastly, we show that the accuracy is comparable to the SPF in the case of core, but more accurate in the case of headline inflation. And just to end here, I would say that this paper actually, the empirical results provide guidance to the practitioners interested in generating density estimates for US inflation. Furthermore, our results indicate that when it comes to density combinations, there is no universal approach that works. And hence, it highlights the importance of examining combination methods on a case-by-case basis. So I will end it here. Thanks.
Okay, thank you, Said. Meanwhile, so if anyone has a question, please go ahead and type it in the Q&A box. Meanwhile, I will ask myself a question, and is this one. So is it basically all about energy? The model that is best capable to predict energy gets an edge, or what?
Yes,
so
okay, thanks, Matteo. So it's a pretty good question. And I would say, yes, for headline, as you can see for core, all 3 are competitive, right? And in the headline, yes, basically from our earlier work, the competitive nature of our modeling, our model from earlier work is the fact that we are doing very good in nowcasting energy. So yes, your intuition is right. And we were actually very explicit in our earlier work. And in this work, we did many exercises, and in our paper and in our accompanying appendix, we do highlight this point that it is the energy, the ability to do very well in nowcasting energy is helping do well for CPI and PCE.
Okay. Thank you. I see a question from Gary Coop. So if please, if we can unmute Gary, it would be great.
Hi, Saeed. Great job.
Thanks, Gary.
It just had me thinking. You made several statements about how flexible these combined predictive densities could be, even potentially multimodal and things like that. Given all the interest in tail risks nowadays, there could be some particular benefits found actually looking forecast performance in the tails of the distributions. Do you think it'd be worth looking at this in a little more detail?
Yes, thank you so much, Gary, for your question. And like I know a year ago, James Mitchell also suggested this exercise. And so have other people's, other few researchers have also shown this, like, the curiosity. We can easily do those. And I was actually hoping for like a short accompanying note using this framework to basically produce those tail risks. But yeah, sure, it can be easily done because we have all these like density estimates. And I would also mention very quickly, Gary, it's like, about inflation, all the, like, it basically comes down to energy. Like when we talk about headline inflation, all the interesting stuff is correlated with what's happening in the energy prices.
Great, thanks.
So there is a question from James Mitchell. So if we can unmute James.
Hi, Saeed. Obviously, we can talk locally about this, so I don't want to take up too much time. I certainly agreed with you that ultimately it's an empirical thing for us to kind of determine in which situations, what type of density forecast combination method works best. But of course, that sort of prompts the question of, can we begin to sort of empirically and indeed theoretically delineate certain situations in which one type of density forecast combination strategy might be preferred to another. So to that end, I sort of wondered, had you empirically looked at how similar the densities from these three classes of mixed frequency model you combine in the grand combination are? That question's prompted by the reflection that we should expect the performance of the combination, as indeed when you combine assets in a portfolio, depends on the correlation structure of the assets in that portfolio. So similarly with the density forecast combination, the properties of the combination depend on how related those densities from the three classes of model are. And indeed one could think of comparing your two-step combination approach with the one-step. We just combine all 100 odd models in one go. So I wondered if you'd tried that as well. Thank you.
Thanks a lot, James, for your excellent question. Yes, I have explored, and in the paper we do provide especially in the appendix, a lot of these extra details, especially about the shapes. And yes, so for core inflation, they are usually very similar. For headline inflation, our model, like, when I say our model from the earlier work, because of energy, and there is this differences in the point, like very significant differences in the accuracy of the point estimates from the dynamic factor model and MIDAS, you do see differences when it comes to CPI, like from the individual ones. There are these differences, and that's why when you are combining them, you get more like a more flexible density, right? For core CPI, as you can see on this on the rightmost upper top right, for core core CPI, they were very similar across the model classes. I mean, the differences are small, and so you could see from that visually that there is not as much, asymmetry relative to for the other three inflation measures. And similarly for core PCE, there is, but not as much as CPI and PCE. So that is like your in regards to the similarity, how differences. That was your first point. The second point you mentioned about was the first stage and the second stage. So haven't done extensive of that, exercises, but did enough to get a sense of that. When it comes to calibration, two-stage helps, because what we are gaining. So in this paper, it's more like, the dynamic factor model, MIDAS and DMS, they are working together to help, complement each other. So the DMS does really good, gets really well the mean of the density, but DFM and MIDAS is helping with the shapes for the headline. So if we do a one single step, the thing is the means are so accurate for our DMS from our DMS models that if we do in one stage, all of the weights would mostly go towards the specifications within the DMS. And it will miss out the contribution that the DFM and MIDAS would have given in basically improving the shape. And what that means is improving the calibration as well. So by doing two-stage, you just like pick up the best ones from the DMS class, and then you have those DFM and MIDAS, which are also getting, some weight. And by providing some weight, you get improvement in the calibration. So overall, what I'm seeing is that for densities, two stages was helping. When it comes to the implied point, there were small differences when you do either one stage or two stage. But for calibration, two stage helped. So I will end here in my response.
I see. That's very, very helpful. Thanks. Thanks, Saeed.
Okay. It's 5:32 here in Rome, so we are a couple of minutes out of our allotted time. I thank Saeed and Shui for her presentation. Everything was great and all the attendees. And I want to also tell attendees that we can carry on our conversation in the breakout room throughout the coffee break. And thank you all. Saeed, do you want to say something to close out?
Yeah, just thanks to everybody. Thanks to you, Matteo, and thanks for everyone attending this session and all the great questions. And we can follow up if you have any questions, further questions with any of the presenters for this session. Feel free to follow up by messaging each one of them, or I think there is a break now, and there is this chat rooms where we could, join and then discuss further. Thank you very much.
Thank you.